We welcome you to our second video on robot controllers, which builds on the basis from the overview of robot controllers video. It covers the core knowledge of robot controller design. In the last video, we looked at the fundamentals of robot control and received an overview in which typical robot control structures were presented. The PD control was also introduced, which we will take a closer look at in this video. We will focus on the physical meaning of the control parameters and how to select them. We will learn about the concept of the kinematic controller and we will see where the limits of the control parameters are. Let's go to know the control parameters of the PD controller. What are the suitable controller settings? The theory and explanations presented here are also suitable for people who did not have an introduction to control engineering. In particular, mechanical engineers can better understand the robot controls through these explanations. Let's look at the mechanical model of a proportional differential controller that is used to position a mass to a specific location. Let us assume that we want to move a mass to a certain position and apply a force to the mass for this purpose. A pointer of the mass points to the actual position. The target position is labeled with XD. We assume that the target position is connected to one plate and that the mass or actual position is connected to another plate. We connect the two plates with a spring constant Kp. In parallel, we also attach a damper. The damping constant is Kd. We refer to the position error between XD and X as position error E and the velocity error between xd dot and x dot as velocity error E dot. The spring force is proportional to position error and is then Fp equal Kp multiplied by E. The damping force is proportional to the velocity error and is Fd equal Kd multiplied by E dot. Putting this together gives the formula F equal Kp multiplied by E plus Kd multiplied by E dot, and we immediately see that this corresponds exactly to the PD controller. As a program example, it would look like this. You can see that Kp of the PD control corresponds to the spring constant and Kd to the damping constant. At this point, you can see that when formulating the controller, the actuator and sensor values should be expressed in SI base units, because otherwise you cannot understand position error, velocity error, Kp and Kd values, and because you lose the relation to physical reality. In the swung out state of equilibrium, the system is at rest. The position error E and thus the spring force is zero. The velocity error E dot and thus the damping force is also zero. The system is force-free. If the system is preloaded, the target position is displaced and the spring is under tension. The control error E is then target position xd minus actual position x and the velocity error is zero. The force F would then be a short moment Kp times E. Due to the force, the system makes a movement. If Kd, the damping constant, is zero, the mass oscillates sinusoidally around the set point value. If the damping constant is greater than zero, the mass oscillates but is viscosely damped and reaches the set point after several oscillations. When the damping constant is equal to the critical damping, the mass reaches the set point without overshoot. The question now arises, how must Kp and Kd be chosen so that the actual value optimally follows the set point? If we look more closely at the forces, we see that the force of the spring Kp times E and the force of the damper Kd times E dot act on the mass and together gives the resultant force F. This resulting force leads to an acceleration which fulfills Newton's laws. The force is therefore mass times acceleration. This system can now be represented as a controller flowchart, which we already got to know in the video Robot Control Overview in the chapter about PD controllers. Newton's equation can be combined with the equation of forces to form a differential equation. To be able to solve the differential equation, we write it out so that the state variable x becomes visible. If you know the theory of the vibration equation, you can continue directly with the derived equations. For the others, I will briefly show the homogeneous solution of the differential equation. Let us consider the differential equation from before. Since we are interested in the homogeneous solution, we set xd to 0. This leads to the following homogeneous differential equation of second order, which looks familiar. We substitute the quotient kd by m with 2 delta and the quotient kp by m with omega squared and obtain the well-known oscillation equation. I assume that x equals e to the power of lambda t, and I derive twice in order to get x dot and x dot dot. After inserting the substitutions into the vibration equation, I can shorten by e to the power of lambda t and thus get rid of my approach. I solve the resulting quadratic equation and get two solutions. If delta is greater than omega, I get two real solutions which I combine with two freely selectable integration constants to one solution. The solutions are two overlapping decaying exponential functions. If delta and omega are equal, I get the solution for the critical case. However, this is only academically interesting because it hardly ever happens in reality that delta and omega are exactly equal. On the other hand, it is interesting when delta is smaller than omega. In this case, I get two complex solutions which I again combine with two integration constants. In the next step, I break it out the decayed e function. However, x1 and x2 must be complex to represent the real x with this equation. This is not very elegant, so I transform the equation again with the Euler formula, and now I can insert two real constants x3 and x4. Since I don't find the formulation with sine and cosine very practical, I reformulate again and now see a damping vibration equation with the start amplitude x0 and the start phase phi 0, with the natural frequency omega 0, the damping delta, and the damped natural frequency of omega d. Please note that the index 0 at the amplitude and the phase represent the initial value at the time 0, while at omega it indicates that it is the frequency of the undamped oscillation. The damping constant delta is often difficult to understand and interpret. I therefore put it in a relation to the natural frequency, which is done with Lair's damping ratio and is very illustrative. If we insert this into the known equations, we see that for a d smaller than 1, the root value becomes negative. The critical damping is therefore 1. If d is smaller than 1, we have damped oscillation. At the beginning of this derivation, we ask ourselves how we would have to set the controller constants to achieve a desired control response for our controlled system. We have now found this. Now we can specify the control bandwidth and damping as desired. The control stiffness, Kp, is then equal to omega squared times mass, and Kd is equal to 2 times d times omega times mass. With critical damping, the mass no longer overshoots in the case of a step response, but the follow-up behavior is slow. Therefore, it is better to choose a d of approximately 0.7 or 1 divided by the square root of 2, because in this case the follow-up response is fast and the overshoot is within an acceptable range. One can use the equation for translation, rotation, or in robot coordinates. Of course, one must use the variables and constants consistently linear or rotational. In the most general case, one forms a vector equation with generalized robot coordinates. In our example, we use translational representation. With these findings, our generalized PD-controlled system looks like this. We can determine and insert the parameters directly from the specifications. For better visualization, we can insert the meaning of the control parameters directly into the control diagram. As a next step, I would like to introduce the kinematic control. We have seen that F equal KPE plus KDE dot, and we can insert the found control parameters. In this equation, we can factor out M. We can also divide the whole equation by M, and since we divide the force by the mass, we get an acceleration as the output signal of the controller. We introduce new control parameters, which are the original ones divided by the factor M. This formulation is called kinematic control because only kinematic quantities appears in the equation. To determine a force, we must multiply the acceleration by the mass. For linear motion, we use the mass, and for rotational motion, we use the rotational inertia. In the general case, we have an acceleration vector, which we multiply by the mass matrix to get a force. This is always in generalized robot coordinates. In the control system, we now see a much more flexible formulation of the PD controller. The dynamics and thus the mass matrix of the robot changes constantly, depending on its position. Finding a good control for this variable controlled system would have been a pain. However, since we have now factored out the mass matrix, the most important changes in the robot's dynamic are taken into account in it, and our control becomes simple. For better visualization, we can insert the meaning of the control parameters directly into the control diagram. The result of our efforts is impressive. The system is very clear and we can design the kinematic controller without knowing much about the robot's dynamic. In most cases, the control parameters are even identical for all robot axes. Since we can specify the bandwidth with the kinematic controller, could we then realize an arbitrary stiff controller? The answer is no. The solution only works as long as our simple mass model for the robot holds true. In fact, this is usually the case if one builds the mechanical structure well in terms of controllability, for example by making the inertia of the robot small compared to the inertia of the motor, and the controller then sees only the motor. However, there is another limit that occurs in every system, which I would like to present here. What prevents us from setting a control bandwidth with 10,000 Hz in our control system? If we look at our controller, the P controller and the D controller each contribute to the acceleration. Let's take a closer look at the Q.ed acceleration. The acceleration Q.ed is proportional to the velocity control error and to the parameter kd. We could also say inversely proportional to a time dt, which corresponds to the time in which the velocity control error would be fully compensated if we freeze the servo acceleration. Since we use digital controls and compute the controller algorithms with a fixed sampling clock, the controller in fact freezes each clock for the duration t clock. If td is greater than t clock, the speed approaches the target speed asymptotically. If td is exactly equal to t clock, the control error is compensated in exactly one control cycle. If td is smaller than t clock but larger than t clock half, the acceleration oscillates widely with a period of 2 control cycles, but the oscillation still decays. If td is smaller than 0.5 times t clock, the oscillation increases until the controller only jumps back and forth between the positive and negative saturation values. It can therefore be said that the stiffness limit of the velocity feedback is reached when the velocity error is compensated in one single control cycle. It can therefore be said that kd must never be smaller than the controller cycle for physical reasons. But where is the limit in everyday reality? What is possible? We have assumed that the control is calculated through every control cycle, from reading the sensor to energizing the actuator. But this is not correct. The algorithms need time to be calculated, and often the inputs and outputs are triggered almost simultaneously to have a common time pace. This leads to a time delay of up to one control cycle. Further time delays are caused, for example, by the numerical differentiation of the position signal. It therefore makes sense to start from twice the value of the control cycle and to add a small safety factor. In my personal experience, I have found that with a factor of 2, a safety factor of 1.15 is usually already sufficient, which is extremely close to the optimal point. Thus, TD must be larger than 2.3 times T clock, respective KD must be 2.3 times smaller than F clock. We determine omega 0 by dividing KD by 2 times D and get F clock divided by 3.2 for omega 0 under the assumption of D equal 0.7. If we calculate the frequency, we find that the controlled bandwidth F0 is 20 times smaller than the controller frequency F clock. So we found that the frequency of the control bandwidth is 20 times smaller than the clock frequency of the digital controller. Omega is 3.2 times smaller than the clock frequency, both under the assumption that 0.7 is used for Leer's damping measure. The kinematic control constant Kp is as known omega squared, and the damping constant Kd is 2 times d times omega. Kd is 2.3 times smaller than the clock frequency. Let's look at an example. The clock frequency is 2 kHz. Kd directly calculated is 470 seconds to the power of minus 1. The controller bandwidth F0 is 100 Hz when using the rule of 20. Kd calculated using omega is 879 seconds to the power of minus 1. Omega is 628 seconds to the power of minus 1. Kp is omega squared and thus 394,000 seconds to the power of minus 2. As a next step, watch the video about advanced robot control and learn about cascaded kinematic controller and controller using the dynamic of the model of the robot. For the implementation, we recommend the open source robotic framework EROS, which we also use in this course. You find it on eros.org or wiki.eros.org. We are happy to answer your questions or suggestions in the forum on Moodle, or if you are not enrolled in the course, in the comments here.